Hello, this is Paul Wasacz from Parts Supercenter. I will be your presenter for today's webinar on troubleshooting control valves used in GE oil circuit breaker mechanisms. Some housekeeping before we start. We will be recording today's webinar and it will be available at a later date on our website. A link will be emailed to each attendee as well as today's slides. We will set aside some time at the end of the presentation for Q&A. You can send in your questions using the Q&A button on the right side of your screen. Please include your email address so we know who to respond to if we don't get through all the questions or if we need to research further to provide an answer. My presentation will go for about 30 minutes today, followed by 15 minutes for questions and answers. In between, we'll talk about how control valves work, how to set them up, and what to look for when troubleshooting them. I'll start with an introduction of Parts Supercenter and myself. Parts Supercenter is an OEM parts business supporting four product segments. As shown by the icons on the screen from left to right, the four product segments are transformers, circuit breakers and switchgear, drives and controls, and motors. Many, but not all of these products that we support have roots that can be traced back to General Electric, as we were once part of GE. We specialize in genuine OEM parts. A little bit about myself. Again, my name is Paul Wasacz. I am the product manager responsible for General Electric Magnablast switchgear and oil circuit breakers. I have more than 30 years of experience with circuit breakers and switchgear, and I'm pleased to spend some time this afternoon with you to discuss control valves used on the pneumatic operating mechanisms of GE oil circuit breakers. Parts Supercenter has been the licensed OEM for the Magnablast and OCB product line since the GE factory that was located in Philadelphia closed in 2002. Parts Supercenter, or PSC for short, has the care and custody of all the intellectual property related to the design and manufacture of the GE Magnablast and oil circuit breaker product lines. We are exclusively responsible for the manufacture and sale of all the OEM replacement parts, as well as all engineering support and equipment modifications for the Magnablast and OCB lines. That's all for introductions. Let's talk about control valves. The control valve, a photo of which is located on the right-hand side of this slide, is an integral part of an oil circuit breaker. It's the device that initiates the flow of air from the air receiver or tank in the mechanism to the piston that does the work of moving the linkage to close the breaker. You will often hear it described as a closing valve. It contains a coil that operates the pilot armature within the valve, and that coil is often referred to as a closing coil. You could see that the valve is bolted up to plumbing within the mechanism in the photograph. The control valve is located in the mechanism cabinet, which is usually located at the end of the circuit breaker, or in the case of single tank oil circuit breakers, it's located in the mechanism cabinet that's fastened to the framework that supports the circuit breaker. In the picture on the left side of the slide, you can see the red arrow pointing to the control valve. It's sandwiched between the air supply line that's coming from the air reservoir and the operating cylinder. That's directly attached to the linkage that drives the circuit breaker to the closed position. Like just about any other electromechanical device, in order to be able to set up a control valve or even troubleshoot a control valve, you need to understand how it works. We're going to start by talking more about the complex control valve that's used on the majority of the mechanisms in service, which has 3 independent windings in the control valve coil. Let's start by assuming that the circuit breaker is in the open position and the air receiver is fully pressurized and that the circuit breaker is sitting idle awaiting a signal to close. The flow of air is shown by the red arrows entering the control valve from the left side as the valves are oriented on this slide. The air is filtered as it passes through a 2-layer screen, part number 29 on the illustration, before entering the bronze valve body. The photograph on the left shows a window cut into the control valve, while the line drawing on the right shows the valve sliced into a section view directly down the midplane of the valve. Now let's zoom in and see where this air goes within the control valve. As the air passes through the screen, it quickly fills the chamber and wraps around the center section between the two lobes of the main piston, which is item 13 in the lower valve body. The main piston is free to move vertically up and down in the lower valve body. It's being acted upon by the air pressure upon all the surfaces between the upper and lower lobe of the main piston. Since those surfaces are approximately equal in area, the piston will tend to stay in place. In addition, above the piston, there's a bias spring. It's item 11. That's applying force in the downward direction, helping to keep the main piston in the down position against the seat in the lower valve body, preventing air from passing through the valve where it would attempt to close the breaker. In addition to the spring above the piston, there's one more force acting to push the piston down, thereby keeping the flow of air from passing out the other side of the valve. That additional force helping to push the piston down is generated by the small bleed hole in the top of the piston. This hole allows the air trapped between the two lobes of the piston to escape to the area above. Since the air pressure acts in all directions, it will push down on the large surface area on top of the piston. The net effect will be a strong differential pressure in the downward direction from the air acting on top of the piston plus the bias spring above the piston. The forces acting between the lobes cancel each other out since the surface areas are similar in size. Now remember again that the air pressure works on all surfaces and the resultant force is proportional to the surface area. So we also have force pushing against the underside of the pilot armature, item number 10, which also has a spring bias above it. I visually represented this just left of center of the page with the red arrow pointing and pushing up on the ball at the bottom of the pilot armature. Let's take a closer look at how that bias is applied on the next slide. Since the surface area of the ball at the bottom of the pilot armature is so small, it's easy to tune the spring bias above the pilot armature such that no leakage will occur between the ball of the pilot armature and the pilot armature seat directly below it, which is item 25. Additional pilot armature spring bias is obtained by additional shim washers, item number 1. In the line drawing on the left side of the page, the shim washers are shown above the pilot armature bias spring, which is item number 3. On the left side, the photograph shows the shim washers below the spring. They can go in either position, and it's easier to reassemble the valve with the shim washers on the bottom when reassembling. Let's talk about how the valve opens and allows air to pass through in order to close the circuit breaker. When we want to close the circuit breaker, we need to open the control valve to emit air to the cylinder that's connected to the breaker linkage. This is done by energizing one of the 3 windings in the closing valve coil. By allowing current to flow through the VC winding, which is item 7 in the line drawing, the pole piece, item 22, becomes permanently magnetized and generates a flux in that 65 thousandths air gap between the pole piece that has been magnetized and the top of the pilot armature directly below it. The resultant magnetic field will lift that pilot armature and close up that 65 thousandths of an inch gap, overcoming the pilot armature spring bias above. So the next slide will show graphically how that pilot armature looks in the raised position. In this slide, we've energized the VC winding, which is the close winding, which will have the effect of permanently magnetizing that pole piece and lifting the pilot armature against it. On the left, you can see that the pilot armature gap of 65 thousandths no longer exists, and the ball at the bottom of the pilot armature, it's no longer resting upon and sealing against the pilot armature seat below it. On the right side of the slide, you can see that the air is now passing the pilot armature seat through the center and going up and out the circular array of holes that allow the air trapped in this area to escape to atmosphere. Note on the right illustration, there's a green oval near the bottom of the valve body. This is the exhaust port on the valve, which is always open when the valve is closed. When the exhaust port is open, it evacuates any air that could be trapped between the outlet side of the control valve and the cylinder and the mechanism that drives the linkage to close the breaker or open the breaker. So the piston in the lower valve could really be called double acting. When it's in the lowered position, forced downward, the exhaust port is open and the valve itself is closed. When the piston is raised, the exhaust port is shut off and the valve is open. Let's move to the next slide to see the piston and the valve body move to the open position. The piston is now lifted due to the negative differential pressure above it, and the exhaust port's now sealed off. So air is being admitted directly through the control valve to the main cylinder of the circuit breaker in an attempt to close the circuit breaker. As the circuit breaker approaches the completed closing stroke, an auxiliary switch or mechanism auxiliary switch will interrupt the flow of current to that VC winding in that closed valve coil. Let's see what that looks like on the next slide. The auxiliary switch contact or mechanism operated contact has interrupted the current to this VC close winding, and another auxiliary switch or contact or mechanism operated contact has now energized the cutoff winding, VCO. This winding has the reverse polarity of the close winding, and it's there to demagnetize the pole piece that we permanently magnetized earlier, allowing the pilot armature to drop and seal on top of the pilot armature seat under the influence of the pilot armature bias spring above it. If we didn't have this cutoff winding, the pilot armature would continue to be raised even though the current was cut off from the close winding VC. Notice that the 65 thousandths armature lift gap is reestablished and the pilot armature seat is now closed off. However, the main piston is still in the open position, allowing air to be passed through the valve, while the bleed hole allows air pressure to be reestablished above the piston in order to push it back down and seal off the main valve. Let's move on to the next slide to see this in action. An auxiliary switch contact or the mechanism operated contact has interrupted the current now for the cutoff winding VCO, now that the circuit breaker is closed and latched. So the piston in the control valve is now in the closed position, shutting off the flow of air through the valve and opening the exhaust port at the bottom of the valve. The control valve is back to a steady state and the breaker is ready to trip if necessary. Before we go through the trip operation, we need to consider one other scenario, and that is if the breaker should need to trip free if it closes in or onto a fault. Let's move to the next slide to go through that scenario. So on this slide, the breaker is required to trip free due to closing in on a fault. The VCO cutoff winding is energized, as well as the VTF winding, which is in series with the trip coil. It also, like the VCO winding, has the reverse polarity of the VC or close winding. So both of these windings will be energized in order to quickly reverse the polarity of that magnetic field that's in the pole piece to allow the pilot armature to drop down and seal off the pilot air circuit so that the piston can close in the control valve and shut off the air supply to the circuit breaker cylinder. This will allow the circuit breaker linkage to collapse so that the circuit breaker can trip free. The only possible air leaks, let's talk about troubleshooting. The only possible air leaks are past the main valve body seat, past the pilot armature seat, past the O-ring beneath the pilot armature seat, or past the O-ring seal at the face of the valve on the inlet side of the valve. So if air is leaking past the piston seat, you'll be able to feel or detect it coming out of the exhaust port on the bottom of the valve. You can actually put your hand underneath there and feel it. You can also at times visually, acoustically, you can hear it. It'll make a hissing sound. Or if it's a slight air leak, you can put a piece of paper under there and you'll actually see it blowing as the air leaks out. If the air is leaking past the pilot armature seat or the internal O-ring inside the valve body, you'll be able to detect that at the interface between the upper coil housing and the brass valve body that sits directly below it. If the pilot armature is leaking, it's possible to add slightly more pilot armature spring bias using shims, but there's a limitation in that you have to be careful not to overstress the coil that has to be able to lift the pilot armature against the pilot armature spring bias. So if the external O-ring is leaking, you'll be able to test to detect that leak at the bolted interface using a leak detecting liquid. So you can see in the photograph that there's 4 bolts that attach that flange to the plumbing within the mechanism. To detect the leak between the coil housing and the valve body, you can often wrap a piece of paper around it like a dollar bill. If you can't determine exactly where the leak is coming from, you can do that and you'll actually see the paper deflecting. Or you can use a leak detecting chemical as well, like Snoop. To set up the valve for proper operation, the pilot armature spring bias needs to be set correctly for the operating pressure of the breaker. And also the pilot armature lift needs to be established per the instruction book for the circuit breaker or the mechanism. The pilot armature lift is the first thing you want to set. And you can do this by removing the coil and adding shims underneath the coil housing cap until you achieve the right gap using a feeler gauge through the hole where the coil leads would normally exit. So these shims come in various thicknesses and you will add or remove them till you get the correct pilot armature lift or gap there. The armature lift is normally 0.65 plus or minus 5 thousandths. After you set up the pilot armature lift, the next thing you're going to set up is the pilot armature spring bias. And we set that up by jumpering out the governor pressure switch to achieve a 25 PSI differential above the governor shutoff pressure. Once you get there, you shut off the compressor using the circuit breaker and you check for leaks past the pilot armature seat. So the pilot armature spring bias is properly set when there are no leaks past the pilot armature seat at 25 PSI above the normal governor shutoff pressure. This is all detailed in the instruction book. If you do have a leak, you can add shim washers as shown until no leak exists, but do not add more than 4 shim washers. More pilot armature spring bias isn't necessarily better, as it can overstress the coil in the valve, and it will also disrupt or disturb the timing sequence of the valve if it takes too long for the pilot armature to lift because of the excessive pilot armature spring bias. This concludes the formal presentation, but before I open it up for questions, I'd like to tell you about our next upcoming webinar. Please let us know if you liked today's webinar and found it informative. Our next scheduled webinar will be on DC motor maintenance and troubleshooting on May 27th at 11 a.m. Eastern Time. we will include the sign up link shown on this slide with the emailed files from this webinar. We hope to see you there on May 27th. I'd like to open it up for questions. Rachel, you want to take it away?
Yes, there is currently not any questions. So if you do have a question, feel free to put that in the chat now.
If anyone would like for us to come to their location and train their technicians, we can put this presentation on, and we can also go into more depth. We can get your exact breaker schematic and wiring diagram, and we can go through your particular control scheme and show you exactly how your valve is operating. Rachel, I have a question here. It just came in. The question is, if you have a leak at the pilot armature, is there a way to fix that if the surface is scratched of the pilot armature ball or the pilot armature seat? That's a good question. They are metal to metal seats. So the pilot armature ball is stainless steel and the pilot armature seat is a bronze alloy. We coined those two parts together in the factory when we build these valves. So it's very difficult to reestablish that coining operation in the field. However, some folks have had success doing that. What they've done is they have taken out the springs, the spring rather, that is the pilot armature bias spring, and they've made that solid. And then they've gone ahead and they've reassembled the top cap on the pilot on the valve housing and continued to turn it using the spanner wrench in an attempt to recoin that seat. So folks have indicated that they've had varying degrees of success. I've actually never been able to do it. We have a coining fixture where we take the entire valve coil assembly, put it in a fixture, and then we have a hydraulic press that will match and coin the pilot armature ball to the pilot armature seat. So we haven't had much success in the field doing that, and we would recommend that you replace that whole coil assembly, that top assembly, including the pilot armature seat and pilot armature, if you cannot get it to leak, not leak rather, and if you've established that you have the correct pilot armature spring bias. Rachel, any other questions? Okay, I see another question here. Similar question. What is the best way to fix a leak at the main piston to valve body assembly? So again, this is another metal to metal seal. The piston is a bronze alloy or brass alloy, and the valve body is a bronze alloy. Once again, those are very precisely machined and then coined in the factory, but you have to be very gentle when you coin the piston because it is somewhat of a soft alloy and you can easily bend the piston, and the bottom of the piston will not shut off the exhaust port correctly if you bend it. Even dropping that piston can bend it just enough so that it will not move smoothly up and down in the valve body. So the tolerances on the fit between that piston and the valve body are plus or minus a half of a thousandth. So that's pretty precise considering these were designed and first built in the 1940s, late 1940s. So the instruction books talk about lapping the main piston to the valve body using Clover #4 lapping compound. Again, I've had very limited success doing this myself, but I do have some customers that have told me they've gotten good at it, and have actually created a tool to sit into the top recess of the piston. There's a couple of grooves, and there's a countersink or a counter boss in the top, and they've made a tool to fit into the grooves and the countersink that precisely holds the tool that's spinning the piston as it laps itself against the valve body so that it remains completely perpendicular. So we used to have a tool that we sold to do that job, but it wasn't very precise or accurate. It almost looked like an egg beater or a device that you would use to lap a valve in a car engine, and customers didn't have a lot of success, so we stopped selling that years ago.
Okay, we have another question. How can I adjust the opening time?
The opening time of the breaker is not related to the control valve. So the control valve will change the closing time of the breaker. I'll answer that question, but I'll speak a little bit more about the closing time of the breaker and how it relates to the control valve. So the speed at which the breaker closes is directly dependent upon the volume and flow of air, not necessarily the pressure. So it's really about flow. And so one of the things you want to look for if you're closing slow is that you don't have a damaged coil, you don't have excessive pilot armature spring bias, and that screen that we talked about, that inlet screen on the side of the valve that has the O-ring, you want to make sure that that screen is not all clogged up. That screen has two different layers, a very porous layer to capture big particles, and a very fine screen mesh to capture smaller particles. I have seen where that screen is nearly solid with what looks to be dauber B type of debris in there, like cement. Not sure where it has come from, but most of the time, if it is clogged, you will find rust in there that has come from the air receivers. So you want to make sure that you bleed down your air receivers on a regular basis using the sump at the bottom of most mechanism cabinets. Oftentimes customers will tell me they don't like to do that because the valve on the sump may not seal, and they don't like to do it in the winter as well. But I would argue that you should replace the valve and make sure that you drain the sump on a regular basis so you don't rust out your air receiver, or worse, blow air into the control valve, which not only can scratch that screen, get caught in that screen, but could also scratch the sealing surfaces of the main piston as well as the pilot armature seat. Now, in terms of changing the timing of the breaker tripping, that is primarily done through the tail spring, which is usually at the end of the phase farthest from the mechanism if you have a 3-tank breaker, or if you have a single tank breaker, it would be directly opposite and farthest away from the mechanism cabinet. There are instructions on how to do that in the instruction book. So if the person who asked this question wants to give us the serial number of the instruction book, we'll make sure that we get you that. If you want to give us the serial number of the breaker, we'll make sure we get you the correct instruction book. The other thing that will adversely affect the opening or trip time is more frequently the lubrication in the mechanism. Quite often, the original organic-based greases that were used tend to get hard and oxidize over time. So what we recommend and have been recommending for many years, as most other manufacturers do is to use a synthetic grease. The one that GE has recommended is a Mobile 28. It's a red synthetic grease, and that's readily available on our website. And we can include that part number for that in the notes from this webinar. So I would say that your most likely culprit is not the tail spring. Very rarely is it the tail spring, but that is really the way to change the opening tripping speed. But most of the time it's due to the grease on the trip latch roller within the mechanism. And we can get you the part numbers for the trip latch and the trip latch roller as well if you provide us with the serial number of your breaker. Additional questions? Rachel, I have another question here on how are the valves tested before they leave the factory? So when we build these new valves, we have a test procedure, the same test procedure and the same test equipment and fixtures as we had when the factory in Philadelphia was open. So the procedure to test these valves is what we do is we get the correct series resistors for each of the windings, because there's no way to electrically test these at the minimum, maximum, and nominal control voltages without having the correct series resistors. So that's the very first thing we do, is we obtain the correct values for the series resistors, and then we go ahead and connect up the leads. We have a test stand that we can adjust with a variac the control voltage to the minimum, maximum, and nominal control voltages. So we have a specification for what all of those are, and we go higher and lower than the minimums and maximums to make sure that the valve is going to operate at what the nameplate mins and maxes are. We also vary the pressures. So there's a nominal pressure that the control valve is supposed to operate on. However, the IEEE C30 standard for oil circuit breakers with compressed air stored energy mechanisms from the 50s indicated that you have to have 5 stored operations. So that means that the air pressure will drop to almost lockout pressure on your pressure switches, and this control valve still has to be able to operate and close the breaker successfully. So the standard also says that you have to be able to jumper the low pressure lockout contact and get 1 additional operation. So we go ahead and vary the operating pressures and the operating voltages to obtain the worst possible scenarios and make sure that the valve opens. In addition, there is a timing function that we don't do on every valve, but we do perform occasionally. It's a fixture that fits on top of the valve, and it's actuated by the plunger on top of the control valve, the coil valve housing, and it operates a cycle timer, and it shows that the valve is actually shifting to the open position and closed position in the prescribed time. We don't publish those times because there's no way to really test that in the field. And then finally, the valve housings are hydrostatically tested after they're machined once they come out of the foundry. So we have a test fixture that will generate the appropriate working pressure, maximum allowable working pressure, and we make sure that there's no leaks on the valves since they are a pressure vessel. More questions?
I don't have any questions on my end. Paul, do you have any?
There's one more here that talks about, are these valves able to be remanufactured? In general, we recommend that if you have a valve that is leaking, that you replace it with a known good valve. These valves, as most of the people that have worked on these know, only leak when it's -2 degrees out on a holiday weekend. So we, in general, recommend that the quickest fix is usually to replace it with a new or even a remanufactured valve. We will remanufacture your valve. We will take that back as a trade or as a core exchange and provide you with a valve with the same as a new valve warranty. So when we take those valves back, we will remachine the main seat. We will hydrostatically test the valve body. If it's leaking, we will impregnate it so that it no longer leaks if it's a porous casting, which does happen from time to time. We will provide a new pilot armature seat, a new pilot armature, all new seals and gaskets, as well as a new pilot armature bias spring, and the bias spring that sits directly above the main piston in the lower valve body. So when you get that valve back, it'll also have a new coil, and it should be better than new. It'll go through all the same production tests that a brand new valve would go through. Additional questions?
I did get one question asking if we would send a presentation in a PDF, and yes, we will follow up with an email and a recording of this webinar, as well as the Q&A questions a few days from now.
Okay, there's one more question here, Rachel. The question is, what is the function of the paper washers inside the coil housing? The paper washers sit on top of the coil and keep it from moving or shaking violently when the valve operates. So when you put the shims in, the metal shims underneath the cap that screws on the top, you want to, once you establish the right number of shims, you want to go ahead and adjust the number of paper shims such that you have just a little bit of compression on the valve coil such that it won't shake violently when it operates. Other questions? Again, if anyone would like us to come on site, we can put this presentation on. We bring 12 to 15 control valves, and we let your technicians actually take them apart and work on them. And we practice setting them up as well. So feel free to contact myself or anyone on our sales team. On the final slide has my phone number and my my email address and our sales team phone number. So feel free to contact us if we can be of any further assistance, including getting you schematics and wiring diagrams for your particular breaker so you can do some additional troubleshooting. Rachel, any other questions?
I don't have any on my end. Do you have any?
Nope. I'd like to thank everybody who joined, and I'll turn it back to you, Rachel.
Okay, great. Well, thank you everybody for attending the webinar. I went ahead and put the information for the upcoming webinar, which is May 27th at 11 a.m. East Central Time. If anybody is interested, please go and sign up. We will also be sending a follow-up email with the presentation, a recording, and also a copy of the Q&A. If anybody is interested, please feel free to reach out to us either through Paul's email or through our sales email, sales@pscparts.com, if anybody is interested in getting a quote or figuring out what parts that we should be keeping on hand. So please, everyone, sign up for our upcoming webinar, and thank you for joining us today.